So this is another fun exercise, even if I do say so myself. It's an integral from 0 to pi of sinus theta to the power of 2n. So pause the video and see if you can also have as much as fun as I had with this exercise. So an integral from 0 to pi, that suggests that we can relate this to an integral from 0 to 2 pi, which then brings us to a contour around the unit circle. So basically, we're going to parameterize this unit circle by having z exponential j theta, and then having theta run from 0 to 2 pi. As before, that gives us dz is j exponential j theta d theta, or jz d theta. And then for the sine of for the sine of theta, we know that thanks to Euler's equation, we can write this as z minus 1 over z divided by 2j. So our integral basically becomes an integral over the unit circle of this expression over here to the power of 2n. So it's going to be z minus 1 over z to the power of 2n, and then 2 to the power of 2n, and then j to the power of 2n. That's going to be j squared to the power of n, or minus 1 to the power of n. Let's not forget our d theta contribution. That's going to be dz divided by jz. So now we have this as an integral of this particular integrand here. So now could be a good time to pause the video and see how you can simplify this. Small tip, you need to expand, of course, this particular power to this particular power of 2n here. So let's clean this thing up a little bit. So let's bring out the factors that we don't care about. Well, we do care about them, but they're not inside the integral. So then we have the following. And we basically have z minus 1 over z to the power of 2n. Now, obviously, we're going to be able to calculate that using Newton's binomial formula. So this is going to be a summation from k0 to 2n of 2n choose k, of the first guy, that's z to the power of k. We have z to the power of k, and then we have minus 1 over z to the power of 2n minus k. So that's the binomial formula. And then, of course, we have dz divided by z. So we have 1 over z here, and then we multiply that by dz. Good. Basically, this is here a summation of all sorts of powers of z. And we do know how to calculate those, right? So let's write this in a slightly different form. So that's going to be 1 over 2 to the power of 2n minus 1 to the power nj. And then we can exchange the order of summations and integrals, of course. Everything is very linear. So k0 to 2n. And then we have 2nk. We also have a minus 1 to the power of 2n minus k. But the important part is that we have a power of z, which is equal to, so what do we have in terms of powers of z? We have k minus 1, of course. So we have k minus 1, and then we have minus 2n plus k dz. So all of these integrals should basically be familiar to you, because it's in essence an integral of a power of z and then some junk in front of it. So try and recall what these particular simple integrals were, and then use them to finally solve the integral that we're interested in here. So we know from before that if we have an integral over a circle that's centered around the origin of a certain power of z, that all of these integrals basically vanish, except for the case where the power of z is equal to -1. That, of course, is very familiar in the context of residue calculus. So this term here, so this summation here with lots of terms, the only term that we're interested in is the term where the exponent here of z is going to be equal to -1. So that's going to be happening when 2n minus, it's going to be happening when 2k minus 1 minus 2n is equal to -1. And that's of course going to be happening when n is equal to k. So the only contribution here is the contribution from the term where k is equal to n. And we know that in that case, the result of the integral is 2 pi j. So let's take the final step here. We have 2 to the power of 2n minus 1 to the power of nj. We have 2n choose n minus 1 to the power of n. And then the end result of the integral is 2 pi j. Now comes the fun part. Cancel, 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 cancel. So the only thing so we can simplify this further as being 2n factorial divided by n factorial squared. So this is 2n choose n. And then we have 2 to the power of 2n multiplied by 2 pi. We're almost finished because the only difference is here, what we've calculated is the integral from 0 to 2 pi. What we are interested in is the integral from 0 to pi. But because this is an even function, this is just half the integral from 0 to 2 pi. So the end result here is not 2 pi, but rather pi.